October 21st, 2025. At the moment when 3I Atlas reached the peak of solar heat and the secrets of our third known interstellar visitor are to be revealed, Earth is plunged into blindness. For 6 critical weeks, all telescopes become useless under the blinding light of the sun. This is not just a nightmare for astronomers. This specific time frame is perfect for something that wants to change its course unnoticed. But just before the countdown to 3, Atlas begins to change its trajectory, and the scientific world is engulfed by a wave of shock. The James Webb Telescope captured a ratio of carbon dioxide to water, 8 times greater than any previously observed in comets. Martian flybys discovered a constant asymmetry, and nickel maps created by the KK revealed chemistry that should not exist. What do we not see as the sky descends into darkness? And what will determine if this story ends in December with ordinary scientific data about comets, or a fundamental re-evaluation of everything we know? The sunlight is absolute. When 3I Atlas are behind the sun from Earth's perspective, every instrument, optical, infrared, radar, faces an insurmountable barrier, nearly 1 million miles thick. On October 21st, geometry is fixed. The new moon, the highest conjunction, and the closest approach of the object to the sun, is just 8 days away. For 6 weeks, the sky becomes inaccessible. This is not a technical failure or bureaucratic delay. This is physics. The disk of the sun absorbs the line of sight. Even the most sensitive telescopes, tuned to capture faint signatures from the edge of the solar system, cannot penetrate such brilliance, neither in visible light, nor in radio, nor even with the most modern thermographic images. The darkness is complete, and here numbers are important. At the conjunction, the distance between the 3I Atlas and the sun, as seen from Earth, decreases to 1 degree. This is less than 2 solar diameters. The object's own signal, already weak, is lost in the solar corona, a sea of plasma with temperatures exceeding 1 million degrees. The blind zone extends for 965,000 miles. Trying to observe through it is like trying to see a candle behind a spotlight from the far end of a football field. Even radar, which can sometimes detect objects close to the sun, loses coherence in this chaos of charged particles and magnetic disorder. Mission planners know the calendar by heart. On October 21st, blindness begins. On October 29th, perihelion, maximum solar heating. At that moment, the secrets of the comet usually emerge in the form of gas and dust. This time, the Earth turns blind precisely when the object is most vulnerable, when it is most likely to reveal its true nature. No direct images, no spectra, not even a hint of reflected sunlight. For 6 weeks, the only thing coming from the 3I Atlas is silence. Why is this important? Any change, gas release, fragmentation, even course correction occurs out of sight. The timing is not just inconvenient, it is perfect for concealment. If something wants to change its trajectory without being caught, this is the moment. Blindness is not just an observational gap. It is a test of trust in physics, in models, in the limits of what light can tell us. When the object finally reappears in December, all forecasts, theories, and bets made during this blind period will be put to the test. Until then, the countdown continues, and the sky remains dark. Data matters. Before the temporary shutdown, each major observatory sought to determine what made the 3I Atlas so unusual. The James Webb Telescope, at the urgent request of Dr. Melissa Zhang, captured an object on September the 18th. Its infrared spectrum was shocking. The ratio of carbon dioxide to water vapor was 8:1. This is not a typo. In ordinary comets, water dominates. Here, however, the ratio is inverted and even exceeded by 6 standard deviations. JWST detected strong carbon dioxide, moderate carbon monoxide, and traces of carbonyl sulfide. The isotopic ratios appeared solar, but nothing in the chemical composition matched the usual model. Internal NASA chats reveal how close the data came to being banned. Zhang's team insisted that missing the peak of solar heating would leave the area in ignorance, possibly forever. Meanwhile, the Japanese observatory KK mapped the comet in August and September. Nickel lines glowed brightly. Iron lines were barely discernible. The gas release was not accidental. Gas and dust surged towards the sun, forming a narrow, asymmetrical trail. Reviewers hesitated, fearing that the nickel anomaly might be a mirage or a calibration error. But the data processing confirmed its reliability. No artifacts, no ghosts of instruments. Nickel turned out to be real. Iron was lacking, and the geometry was distorted. The coma stretched nearly 6,000 kilometers in narrow zonal images. The rate of mass loss was about 150 kilograms per second. The water output was only 40 kilograms per second. This is another hint that something in the chemistry of this object and its engine is beyond normal. Hubble images from July 2nd confirmed the assumptions of ground-based telescopes. A wide, smooth, teardrop-shaped coma, rare even among comets in the solar system. No sharp jets, no jagged edges, just a uniform surrounding glow. The core remained hidden, but the analysis of the light curve from the images prior to the discovery at Rubin Observatory on June 21st allowed teams to estimate its size. 5 or 6 kilometers in diameter, it rotates slowly, almost imperceptibly. No sharp changes in brightness, no rapid rotation, just a large, cold, silent wanderer. On October 3rd, Martian resources made their attempt. The Mars Express of the European Space Agency and an orbital probe studying trace gases, managed by the CASAS team under the leadership of Nicholas Thomas, detected an object at a distance of 0.19 astronomical units from Mars. The coma was weak but active, reaching towards the Sun. Images and spectra showed solar activity that continued until the shutdown. Internal ESA records described tense debates about when to publish the data, but transparency won. Public confirmation appeared on October 8th. The geometry of the ejection, chemistry, and light all pointed to an object that does not follow ordinary rules. Each dataset is a foundation. Carbon dioxide suppresses water. Nickel surpasses iron. The shape of the coma is smooth, directed towards the Sun, and stable. The core is large, slow, and quiet. Data about the flyby past Mars confirms that activity indeed exists, and is not an illusion of Earth's atmosphere or a telescope error. These are the traces worth paying attention to. When the object reappears in December, any change, any deviation from this data will have enormous significance. 3 interstellar objects are all we have in our catalog. Of the trillions of cosmic stones and icy spheres wandering through the galaxy, only 3 crossed the solar system while humans watched. The first, Oumuamua, raced by at a steep angle and did not touch any planet. The second, Boris, entered swiftly, high above the plane of the ecliptic. Now the third, Ort Atlas, moves along a path that looks almost scripted, deviating only 5 degrees from the main plane of the solar system, passing between the planets as if it belongs here. The probability of such a coincidence is about 1 in 20,000. It's not impossible, but it's not something that happens every day. Here's how the odds stack up. Most interstellar objects should arrive at random angles scattered across the sky. The ecliptic is a flat disc-shaped zone where planets rotate, and it represents a narrow band. Only a small part of the space coincides with it. For an interstellar guest to enter this plane at such a low angle, more than just a random throw of cosmic dice is required. This evokes interest, but not yet alarm. Astronomers warn against being overly fascinated by a single case. Given that only 3 interstellar objects have been registered so far, each new arrival is seen as an exception. Small selective statistics can be misleading. If the next dozen interstellar comets show similar alignments, then history will change. For now, this is a statistical anomaly, not a conspiracy. The trajectory is not just an angle. The path of I-Atlas brings it closer to several planets. Mars in October, Venus in November, Jupiter next spring. Every close approach provides the opportunity for gravity to alter the orbit and reveal any deviation from the forecast. This is why astrometry is so important before an eclipse. Every data point, every position recorded by Rubin, Hubble, and Mars Express establishes a foundation. When the object reappears after the connection, even the slightest discrepancy, a few angular seconds, could mean that something has changed. Perhaps it's a gas emission, perhaps a fragment has detached, or, as some suggest, something less natural. But before drawing conclusions, mathematics requires caution. The solar system is an active place, and the ecliptic is a natural highway. Even rare events occur if given enough time and objects. It is important not only how rare it is, but whether the trajectory remains true. The December reappearance will become judges. If the orbit matches every forecast, the unlikely path will simply be another point in the growing data array. If not, a serious search for explanations will begin. And until then, the numbers held their breath, awaiting the next move. The sky in October was far from quiet. Solar physicists recorded a burst of activity when 3 coronal mass ejections were launched from the Sun in October. Meanwhile, the world below watched as the auroras stretched far south, green curtains over Kansas and pink reflections in France. Theories on the internet multiplied as quickly as the geomagnetic indices. Some claimed that the surge caused earthquakes, while others insisted that the communication blackout around Tri-I Atlas was not accidental. However, professional reports drew a clear line. The true blackout was geometric, a matter of alignment rather than equipment failure or a solar conspiracy. The sun's glare, not its flares, closed the window for observations. Nevertheless, the timing coincidence fueled speculation. Isabel Ruiz, an astronomy enthusiast from Madrid, published her observations, 17 green comets simultaneously. Her viral post, fueled by impressive photographs of auroras and a list of all active comets, sparked a storm of discussions on astronomy forums. The actual number, 4 bright green comets, Lemon, Swan, K1, and 3 in Atlas, was dramatic but not unique. Experts explain that the cluster of comets is a trick of the Rubin era. Thanks to the nightly observations of Vera Rubin's observatory, dim comets that previously went unnoticed now appear in groups. A shift in detection, not cosmic choreography. Ruiz's enthusiasm was not limited to this. She noted the dim glow following Tri and Atlas in amateur photographs. It could be a fragment, perhaps a satellite. Professionals urged caution. Without astrometric confirmation, any claims about fragments or artificial buffers remain mere speculation. The Center for Small Planets and the Rocket Propulsion Laboratory recorded every reliable report, waiting for the December window for filming. Only then, when the object reappears from behind the sun, will the question of fragments be resolved. An outbreak of space weather in October added chaos to already complex models. The conditions of the solar wind changed with the hours, complicating predictions of the behavior of dust and gas around the object. But there were no instrument failures, no data losses, and no sudden loss of control. Only the relentless movement of charged particles, the familiar chaos of solar maximum. For modelers, each coronal mass ejection and geomagnetic ripple became a new variable, another source of uncertainty for the critical test in December. Ultimately, the surge was real but not culpable. The shutdown was related to celestial mechanics. The excitement of the crowd, viral publications, rumors about fragments, all part of the story. But science firmly stands its ground. The real test awaits when the sky clears, so new data can break the silence. Aviv calls this the scenario of a solar birth. Imagine 3 in Atlas not just as a comet, but as a probe capable of igniting its engines at perihelion, using the gravity of the sun to change course. If this is true, the maneuver will occur in perfect darkness, hidden behind the sun, at the moment when Earth cannot observe. The only proof will be a sudden, measurable deviation in the object's trajectory when it reappears in December. A brutal test in its simplicity. Every major observatory, Rubin, Hubble, JWST, and ground arrays, tracks the object's position with an accuracy of 10 milliseconds. This is the width of a coin visible from a distance of 1,000 kilometers. If 3 Atlases follows the predicted orbit, history will end as usual from the perspective of physics. A noisy exotic comet, no bigger. But if the trajectory changes even by 100 milliseconds, corresponding to a change in speed of 10 meters per second, comet models will not be able to explain this. Gas outgassing, the usual culprit, is too weak and too slow. Only a sudden, directed force can match the data. The main astronomers are cautious. They point to the chaos of comet activity, the turbulent jets, and the uneven mass loss that could throw the core off course. However, the accuracy of this test leaves little room for ambiguity. December becomes binary. Either the numbers will match, or something unpredictable has happened. Lowe's hypothesis is on a knife's edge. Astrometry, not speculation, will determine the outcome. Every pixel, every timestamp, every angular second matters. The countdown is not just the anticipation of a reappearance, but a forthcoming decision. The Rubin Observatory changes the odds. Before the complete cycle of observations, interstellar objects were a rarity, once every few years, if lucky. Now, with nightly patrols and automated processes, expectations turn from anecdotes into archives. Dozens of interstellar objects a year, not a trickle, but a stream. Each new arrival is recorded with precise time, color, and movement, creating a dataset that turns exceptions into statistics. The next time the hyperbolic visitor crosses the ecliptic, it will not be the only headline. He will become one of many, compared with the growing catalog. This is the future of interstellar object science. Every orbit, every gas emission ratio, every fragment trace is measured, compared, and analyzed. Patterns that once seemed suspicious, such as low angles of inclination or close passages to planets, become verifiable rather than just discussed. The same applies to chemistry. 6 sigma ratios of carbon dioxide, nickel comets, droplet-like luminescence. With enough samples, the boundary between rarity and routine becomes clearer. Discipline shifts from individual studies to population analysis. Rubina's achievements concern not only numbers. Time is also important. Early detection provides more time for responding with space assets, more chances to capture activity before and after solar heating. Coordinated campaigns, Mars orbiters, Hubble and James Webb telescopes, as well as ground networks can now respond faster, track more objects, and fill gaps left by geometry or weather. What was once chaos becomes a system. The mystery of the 3 atlases, whether an anomaly or a new archetype, is already part of a broader change. The dam is open. The next decision will not be the last. The reappearance in December will test whether its orbit matches predictions or shows unexplained changes. If the trajectory remains unchanged, it will confirm the existence of a natural, albeit unusual, comet. Any deviation may require new explanations and urgent subsequent actions. While observations like Vera Rubin's prepare to find dozens of interstellar visitors each year, the current lull highlights both our achievements and our limitations. At the moment, the Tri-Eye Atlas project represents an example based on hard facts, open questions, and hope for answers that remain out of reach.